Right. So now let's remember this chapter, internal convection, right? So this is internal forced convection. So basically the problem that we are solving is there is a flow into the pipe is sitting at Ts, the flow is coming at T inlet, leaving at T exit, and he will ask you to calculate the Q or some kind of thing related to the Q, the area of the pipe, the Q, the temperature at the exit of the pipe. It boils down to calculating the flow rate, the heat transfer rate, or Q, which is H A delta T, right? And we talked last time that it should be logarithmic mean. That's actually more accurate, right, rather than the arithmetic average. It's always more accurate to use logarithmic mean temperature difference. And the whole chapter is about really the H, how we can come up with that H. And the H come in form of Nusselt number, this guy, which is H length scale divided by K. And the difficulty in the exam on Monday would be to basically, out of all those Nusselt number, there are tons of them in those two chapters, which one would you pick? So that you calculate the H out of it and then say Q is HA delta T. That's the difficulty. Just nail which Nusselt number we should use. And the problem will be solved if you actually read the title of each section. So this would be turbulent flow, this would be laminar flow. Later I will tell you, here's the flow in an annulus. So that's basically flow between two pipes. Right? So just get your hand on the right section. And within that section you may also see some division, like here is the flow for turbulent pipe, but here is the flow of turbulent pipe but liquid metal. Alright? So let's read the section, and that will help us to nail the equation. Right? So for example, we finished with this last time, and we said this is the equation for the Nusselt number, and this power was 1/3, but then later in this correlation by Ditz and Poulter, they said, well, it actually get more accurate if this 1/3 become 0.3 for cooling and 0.4 for heating. And we will solve an example in a minute now about this. Right? And if the temperature at the surface is very high or very different compared to the fluid, if TS is just really way different than the flow temperature, this is actually more accurate, right? Where you would have correction of, so it's the still 0.8 parental 1/3, but the power is the coefficient is a little bit different. Now it's 0.027 multiplied by mu over mu s or 0.14. And I told you all those are experimental, but they have some theoretical part inside the way they are formatted. Like, why did they multiply this by mu over mu s? Well, there is a theory behind this. They realize that if the wall is really, really hot, it will change the boundary layer. What kind of change? Well, the flow would be a little bit different. Therefore, it's the viscosity that would really do this. And so that's why they say, for example, let's multiply by mu over mu s. And then they will get this power and that coefficient from the experiment. Once they formulated what are the key player, they just said the experiments have different pipe, different temperature, and they always try to measure the Nusselt number, and they correlated with those key player in their mind, and they get the best power. Okay. And there is even a better correlation. So this is actually for air less than 10%, but those are the ranges that are associated with them. So you can see let me get my hand here. So for Reynolds between 10 to power 4 and 5 to power 6, this is less than 10% error, and this one 3 to power 10 to power 3 all the way to 5 to power 6. So which one would you choose? So if the Reynolds number really it's within this range, this should be good enough. So in the exam, if I tell you the Reynolds number and you pick a correlation that's around that, or it's valid for that range, you are free. You are set. You don't have to worry. But if the Reynolds number was 5 to power 10 to power 3, 5,000, and you end up using this, and you ignore the fact that, well, this one is actually more appropriate for that range, then you lose points over it. Because you didn't make sure that the range where this correlation is validated, you ignored that fact that it starts working up till 10,000. So if the Reynolds number is 5,000, maybe you should actually use this one. All right? So that's the only difficulty. And this is for liquid metal. So again, if the problem has liquid metal, you just have to use this one. You cannot say, but wait a minute, it's liquid metal, but my Reynolds number was in that range. Well, probably that works for your number, but you didn't check the Prandtl number. So the Prandtl number here is different from that range, because that's for a liquid metal. Right? So just make sure that the correlation that you choose is appropriate to the range of the condition you are trying to solve the problem for. Right? The Reynolds number is correct, the Prandtl number is correct. And you'll be done. You just get the Nusselt number, and from that you get the H, and you would say Q equal HA delta T, and then figure out, does he ask for the Q or the delta T or the area? And we said last time, if you ask for the delta T, that's the worst problem ever. Because the properties require delta T. So it's just basically a lot of trial and error, if that is the case. So here is the liquid metal, and those are two correlations. One, when we know TS is constant, then this would be best. And this one is when QS is constant. So they are sending the same flux everywhere, and as a result, you guys know that TS would be increasing along the pipe. So for rough surface, you think the heat transfer would improve or decrease? It probably will increase, right? Because that rough surface basically, yeah, makes it turbulent. And even if it's turbulent and you have this also roughness, it really helps break the boundary layer, right? Help basically bring the gradient closer to you. So anyway, here he calculate the friction factor. I'm not going to ask you to calculate the shear stress for me, right? But know that there is correlation to calculate the shear stress in term, or the pressure drop. They are two faces for the same coin. And the way to calculate this is basically F, the friction factor. Remember from the Moody chart? For laminar pipe, it was just how much was it for laminar pipe? As function of Reynolds, it was 64 over the Reynolds. But for turbulent pipe, there was not just one curve, there were a bunch of curves. And those were for different epsilon over d. Depending on the epsilon over d, the friction gets bigger and bigger and bigger and bigger. Right? And here is a correlation that describe this. Right? So this is called Coulbrook. And it can give you the F if you know. So according to this graph, what do you need to know the F? You need the Reynolds number and the epsilon over d, right? And this is what you see. You actually see the Reynolds number, and here is the Reynolds number, and here is the epsilon over d. But what else do you see? Right, the F is also an equation. That's horrible, because that makes the equation implicit. No, not insoluble, but implicit. Make it implicit, meaning the solution is there, it just, you have to do it by trial and error. Alright? And that's my idea to tell you how to solve by trial and error. You basically assume an F and you calculate an F. You are hoping that when you assume an F, you end up calculating exactly the same F. Or basically, as you hope you intersect that line, the 45-degree line. So graphically, you know, if you assume this and you get this, and then you say, oh, that's not correct, let me assume this, and then you end up getting this, then all you have to do is just connect a line and say, I bet the solution is between them. Okay. So I remember when I was a senior student and we had this heat exchanger problem, but the equation at the end ended up having implicit form. So what I was trying to solve for, I forgot what I was trying to solve, whether what was the temperature or the Q. But the equation had that thing in in the right hand side and left hand side. So I said, let me just try and iterate on it. So I iterated. So I assumed, say, 5. I end up getting 10. So you are tempted to say, well, let's put 10 again. I end up getting 5. So I told myself, the iteration is not done. The iteration is done when you assume something and you get the same something, right, from the other side. So here you assume, say, 0.1, and you calculate from here also 0.1. If you assume 0.5, you get 0.8, and then you assume 0.8, you get 0.5. This will never end, right? Then what? So I realized that I was basically, it was such that it was like in a peak. So I said to myself, it must be in the middle, between 0.5 and this thing. So I put it in the middle, and then it came really, really close in the middle. So I said, I'm done. So it was really, and you are terrified because the time is ticking, and you have to finish the iteration before the exam is over. Anyway, people don't like implicit method because of this. So there is actually explicit method, right, to actually to solve this. Of course, it's not as accurate as the implicit method, right? But it's nice that it's explicit. You just plug in epsilon over d and the Reynolds number, and you get your F. And actually, as part of my senior design project as an undergrad, we were designing a pipeline connecting a crude oil pipeline, connecting basically the Red Sea to the Mediterranean Sea, right? It was actually there, the pipeline, but the company was extending it, making another pipeline. So we are kind of checking on their calculation. So it was really nice. I mean, the design was already being done, and we were just trying to do it again. And as part of our project, the professor told us we need the friction factor. There are tons of those correlations. He said, collect all the friction factor correlation in the literature and figure out which one of them is actually more accurate. And so, of course, the explicit method was really very convenient because you can check on it very easily. And so we tried one of them, and it was like completely off the chart. And so we were like, how is that possible? And so we actually we got it from our undergraduate fluid mechanics book. It was Fluid Mechanics by James, S-H-A-M-E-S. And so we called the guy. He was a professor. He was still actually in living at that time. And we called him and we said, well, the equation is wrong. And so by that time, actually, you contact him by sending a mail. And so the mail came back to us, and he said, yes, we fixed that in the next edition. There is actually another bracket missing. So that was all what's missing. But when the bracket is missing, that make the multiplication basically kind of summation, and it was like completely off the chart. But anyway, we were like, what? Just a bracket? We thought that we found like something really big. Anyway. All right. So again, I'm not going to ask you to calculate the F, but just know that you can calculate the F if you want. Right? What do you do with the F once you calculate this? So probably I will give it to you in the exam. I'll tell you F is this much. What you do with it is you calculate the pressure drop. So delta B is, if you remember from your fluid, what is it? The delta B friction, F L over D half rho V square, right? That is the pressure drop because of the friction. And that F come from this chart or come from the correlation or be given to you from your instructor in the exam. All right? And of course, what's the unit of that delta B? Pascal. If you stick to SI, rho is kilogram per meter cube, V is meter per second, this guy will end up being Pascal. Because of course you know that half rho V squared, that's the dynamic pressure already. And F L over D, that's dimensionless. Right? So I also remember in that senior design project, so we were trying to figure out what is the right diameter for the pipe. So of course you realize that if the pipe is really very big, it would be very expensive. The bigger the pipe, especially that pipeline was like, it was really, really long. So the bigger the pipe, the more expensive it is, right? Not just the pipe, but the valves connecting it and the fitting and all the protection, because you're supposed to protect it against water hammer. That's when suddenly a valve could close, the pressure would rise, and the pipe would rupture, right? And so you had to put a lot of relief valve and stuff, especially because it was crossing a river. So if you end up exploding in the river, you'll end up losing a lot of money paying for compensation cleaning so you have to protect against basically explosion inside the river. So the bigger the pipe, the more expensive, right? The smaller the pipe, it will be cheaper, but what will go up? And therefore, the pumping cost, right? So you'll end up paying, you are not paying for the pipe up front, but you'll keep paying for the life of the project for the pumping work. The pumps, because of the friction loss, you'll have to spend a lot. So we were trying to figure out what is the most economical diameter. There must be a sweet spot where the pumping cost go down and also the price goes down. So we were trying to collect different pipes, sizes, and see their prices, and see basically how much they will cost if we actually build it out of this particular size. And to our surprise, when you buy or in the manual or the catalog, when you try to purchase the pipes, when they say the pipe is 1 inch or 10 inch, that 10 inch is not. So a 10 inch pipe or 4 inch pipe nominal size, that's not the inside diameter, and it's not the outside diameter. I don't know what it is, really. So you have to open the catalog to figure out what is the inside diameter for this 10 diameter pipe. All right, so there is this one problem that I had last year. I think when I told them 1 inch nominal size pipe. So the one that assumed this is the diameter, no, it's not. They lose point. They actually have to go here in this table and say, 1 inch, then the inside diameter is this, right? Now the schedule 40, schedule 80, schedule 10, that's basically the thickness of the wall, all right? So knowing the nominal size, so there is another table like this for schedule 80, for example, and schedule 10, all right? So the schedule will give you the thickness, and that table will give you the inside diameter, right? And of course, you add the thickness on it, you get the outside diameter of the pipe. Now you have those two diameters. And this table is for different epsilon for different material. All right. Actually, should we? Let's solve a problem now. This is a problem we solved last time. All right, so there is this pipe, and actually I just remember one more thing I wanna say. So last Monday when I uploaded the lecture, the next day the lecture were deleted from the Dropbox, and distance learning told me where is the lectures, and so I had to upload them again. So I'm going to upload the lecture today, and if the lecture are deleted from the Dropbox, I'm going to delete all of you from my Dropbox. Okay? Don't delete the lecture. Copy and paste. Don't cut and paste. Okay? If you do it accidentally, that's okay. Email me and tell me. Don't let us wait until distance learning tell us that you deleted the lecture. Thank you. All right. So this pipe has, where is my red pen? Has 5 centimeter diameter, and he actually didn't say whether it's inside or outside. He just said pipe diameter is 5 centimeter. Okay, so I don't know whether it's inside or outside. And there's a fluid going in, and that is air, and the air is moving at 20 meters per second and 1 atmosphere and 325. Its bulk temperature is 325 degrees C. Flow with a velocity of 20 meters through this pipe, while cooling ambient air, so the air here, the cold air, is going around the pipe, and that air is moving at 40 meters per second, and its temperature T infinity is 25 degrees C. Alright? And he said determine the heat loss per unit length of the pipe. So required is Q per unit length, watt per meter. So that thing per unit length, if it's confusing to you, just say, so he wants me to solve it for 1 meter of the pipe. That's per unit length. So assume we have 1 meter, and he would like to get this Q. Alright, so what is the solution? How can I get my Q? Anyone? Which there are, is there only one H or two H? So why there are two H to start with? Right. There are H from the inside and there is H from the outside. Right? And just like when we had multi-wall in our first exam, multi-component wall, remember there was like 3 component and the temperature were given in the 2 extreme ends of the walls, and he calculated he asked for the Q, and we said the Q was delta T over R. It's the same thing. You have T infinity and you have T bulk inside. There is fluid inside, there is fluid outside, and the Q that will happen between the hot to the cold must be delta T over all the resistance. And there are 3 resistance, 2 convection and 1 conduction. Right? So the equation that we have here is that Q dot, and actually before I write the equation, let's make a cartoon of what's going on. So there is this T infinity, and then there is a resistance, and then there is conduction, and then another convection, and here is T bulk. And so this would be 1 over H in area in, and this would be 1 over H out area out. And the guy in the middle, that's the conduction of a pipe. How much is that? Does anyone remember the conduction of a pipe? X ln R2 R1 over 2 pi KL. However, in that problem, right, so that's the cartoon, right? And the Q that we are trying to calculate is the Q that's going to flow like this, between the hot to the cold. And I didn't take back what I said, that those problems will be solved by Q equal HA delta T. It's just that we have 2 HA delta T. Right? So if you're doing this part only, sure, that Q is delta T over, it's HA delta T. And if you are doing this part, it's still Q is HA delta T. But now because we have, they are in series, the two resistance are in series, we have to say that the Q is the two temperature extreme over the total resistance. All right? So it's exactly the same procedure. Guess where we are going to get those H's? Huh? Nusselt number and the Nusselt number come from one of those correlations. Let's hope we pick the right correlation. So we'll pick the right correlation for Nusselt number and calculate the H out of it. And therefore we have Q equal HA delta T, or let's just say Q is delta T over the total resistance. Why cannot just say Q is HA delta T? Because yeah, but can I just do it from here to here? I could just say it's convection, Q is HA delta T. What's wrong with that? It's that temperature minus, we don't know that surface temperature. Right? We don't know the surface temperature. That's why we will just have to really do the whole thing. Because when we do the whole thing from the right to the left, the surface temperature disappears. We don't care about it. Okay? So that's the solution strategy. You will understand the solution, I'm sure, because it's very simple. But it's why did we do it this way? That's what's important. Why we just didn't say Q is HA delta T? Because I don't know the delta T for each one of those convection. All right. Furthermore, in this problem, he never said what's the inside diameter and what's the outside diameter of the pipe. He didn't even say what is the K of the pipe. So what should I do? I mean, if I give you this problem in the exam, a lot of you will come and tell me, well, we don't have the K, what should we do? And I tell you, I will not be able to answer that. And then a bunch of you will say, well, let's assume that the K is 0.4. I don't know why, but. So that's not the solution, the K is 0.4. What is the solution if this show up in the exam? But we didn't, that's if you know the material. If he said it's a copper pipe, he didn't never say what is the pipe. What do you mean by constant heat flux? If you are saying that the Q through the convection is the same as the Q through the conduction, the same as the Q through the convection, yes, that's correct, because it's the same Q everywhere. My question is, when I say this delta T, let me recap my question. So TB minus T infinity over 1 over H out, area out, plus ln R2 over R1, 2 by KL plus 1 over HI, area I. I will get this HI and H out in the next page from the Nusselt number. But wait, Jesse. And I know TB and T infinity. My question is, to get that Q he asking for, I need R2 and R1 and K. So what should I do? Yeah, why?
Because it's small.
Right, because conduction, that's excellent question. And I keep forgetting your name. Del, that's the easiest name you should ever remember, right? It's like, it's here, it's right in front of me. So Del is saying you should neglect it because it's very small, and it's very small compared to convection. Conduction is very small compared to convection, especially if it's a pipe done for heat exchanger. This is not an asbestos pipe or plastic pipe. If they are using it to cool with outside air, probably they did their homework and they pick, a metal pipe with very high K. Right? They are not going to make their cooling pipe out of plastic with very small K or insulating material. So we will neglect it compared to the two other resistance. All right? So you would say neglecting conduction or R conduction. And so can I do this on you on the exam? Can I actually give you a problem and then make you neglect stuff into it? Well, let me remind you, when I was a junior student taking my vibration course, we had this new professor. He came from MIT, he had his PhD from MIT, and that was the first course he taught, actually. And so that was a vibration problem, and so, you know, he was trying, the street has the sine wave in it, and then the car damping system was modeled as a spring with a damper, and then another spring. It was like a really complex geometry, complex mechanism connecting to each other, and eventually he said, if the street is bumping like this with this disturbance, what happened to the passenger? So you write the system equation, and you have the input, and you try to get the output, and you probably know from system that you need to integrate to get this. And so I kept integrating, and I was a good student in the class. He knew that I was really the best student in the class. And so out of like 150 students, he kept coming to me and checking on my solution to see what I'm doing. And so I'm very nervous because I don't want to solve my problem alone. You know, I don't want anyone to pick on me while I'm solving the exam. And the problem wouldn't really integrate. You keep integrating it by parts, and it doesn't show up exactly the way it should be, so that, and I'm like a good student, I will have to finish this problem. I will just keep neglecting it. I will keep trying to integrate it. And then, like after half the exam was over, you know, and he saw that if this guy cannot solve it, probably the other guy didn't too. So he said, if you are really good engineers, you would know how to simplify the problem before you solve it. And like, what? Can I re-simplify the problem? So if you say, this damper, I think it's not going to do anything, I can neglect this, then the problem just become a spring damper problem. Or something like this. In this heat transfer problem, you would say, that conduction, I bet it's really, really small. I can neglect this, especially that I don't have the information for it. When I was a student, in my defense, he gave us everything. So, you know, I felt that I'm really obliged to solve it. I couldn't really neglect this part. But anyway, so I ended up getting 16 out of 20 in that exam. But anyway, I still remember actually. Because it was the highest, but still I was very disappointed. I never got 16 out of 20 when I was a student. So my point is, yes, at that level, the end of the story is that at that level, yes, we expect you to be able to say, my answer will not change that much if I cancel that term. All right? Because eventually, as an engineer, your job would be to model the real life problem in a mathematical form. And every time we do this, we do a bunch of simplification. And you should be able to do the right simplification, because you could simplify too much, the problem is basically destroyed. All right? So you could say, well, let's neglect the outside convection. No, you cannot. I mean, by this you would say, let's assume that the surface temperature is 25. So you just neglected the outside convection completely. Right? If you neglect 1 over h out, area out, you'd say it's just very, very small resistance. You would just make Ts equal to 25. All right? So long story short, yes, I may expect you to simplify the problem by yourself, especially if things are not given. All right? And if you simplify it such that the final answer is good enough, you shouldn't lose any points. But if you simplify too much, you destroy the final answer. No, that's not correct. All right? So now, after neglecting this, so basically all our job now is to get the HI and H out. All right? So for HI, that's a flow in a pipe. So we should check whether it's laminar or turbulent, so that we can pick the right correlation, right? So how can I check whether it's laminar or turbulent? Reynolds number. And so to get the Reynolds number, I need properties, right? I need the viscosity and so he said that the flow, actually, by the way, when he said the hot air in the middle, inside the pipe is at 325, he actually never said whether it's the inlet or the outlet. So that's actually even more convenient. He's just assuming it's around 325. So if we were given the inlet temperature, as we will see in the next problem, we expect the outlet temperature to be a little bit different. And therefore we expect the fluid property, the viscosity and all the stuff that we would need, to be evaluated at the mean. Not the inlet, not the outlet. The pipe would be sitting in the middle. The fluid in the pipe would be sitting between the inlet and the outlet. But over here in this problem, it's just too simple. He said the fluid is at 325. All right. So 325 degree C, that's 598 K. That's T bulk mean, or basically that's T inlet plus T exit over 2. All right. So for air at that temperature, I get my nu 5 10 to minus 5 meters square per second. The Prandtl, why do I need the Prandtl? Because the Nusselt number usually have Reynolds multiplied by a Prandtl. So always get new Prandtl, and what's the third thing that when we go to the table for those convection problem we need to get? K, because the Nusselt number has K into it too. So the Prandtl is 0.693 and the K is 0.0457 watt per meter Kelvin. And therefore now we can calculate the Reynolds number, and so the Reynolds number is Vd over nu, so that's 1.9 10 to power 4, which make it laminar or turbulent. That's 19,000 turbulent, because the turbulent, right, the laminar finish at 2,300 and turbulent start at 10,000 officially. 10,000 in that textbook, turbulent start at 10,000. Right, so that's 19,000. We are turbulent. All right, so let's check the turbulent equation for a second. So the turbulent equation was, and so he didn't say we are actually cooling. The pipe is cooling the fluid. So we should use the 0.3, not the 0.4. Right? So it's going to be 0.023 Reynolds to power 0.8 Prandtl to power 0.3. Okay? So I'm going to say that the Nusselt number is 0.023 Reynolds 0.8 Prandtl 0.3, because the TS is less than T mean, T bulk mean. So we are cooling the fluid. Okay. So you got the Reynolds, you got the Prandtl. The Nusselt number is 54.6, and that Nusselt number is HID over K. Right? And whether it's DI or D out, we don't really know what's DI and D out. He just gave us a diameter, 5 centimeters. So I guess you can just assume the thickness is small, that this diameter is good enough for both of them, inlet and outlet. So assuming DI is the same as D out is the same as 5 centimeters. Alright, so this D is 0.05, this K is given 0.045, you'll get HI as 50 watt per meter square Kelvin. Question? Yes?
Why did we use the temperature film like we had sometimes before and after?
Right, and so remind me again of your name, I'm sorry. Cameron said when we get the properties in the previous chapter, we use T-film, right? Which was Ts plus T infinity over 2. All those external heat transfer problem, flow around the cylinder, flow around the sphere, right? Flow over a flat plate, we use T-film, right? And as I told you, we don't really have a choice what to choose as a temperature. We just have to follow the recipe that they use to cook that formula, that correlation. So if the correlation says use T infinity everywhere except for mu s, use surface temperature, we do this. If they said use T-film everywhere, we use T-film. In internal flow, they actually use the fluid temperature, the bulk temperature. So in those formula, the properties is not at the film temperature, the property is at the bulk temperature, right? The average bulk temperature.
Why do we have to use Kelvin this time?
No, that Kelvin actually just for the table. So I guess the table that I used had Kelvin in it. So if the table is reading degree centigrade, go for it. If the table is saying Kelvin, is it degree C? All right. I guess the table that this problem came from. So this problem was from another textbook, and they actually used the table that has K in it. And also, if you check the table and you come up with different nu and Prandtl number, don't panic. Sometimes the process is not the same exactly from different textbook. That's okay. You will be judged against this textbook in the exam. All right. So what's next? We got HI. What else we need? H out. And so that is external heat transfer problem, flow around the cylinder. And here, when we use that correlation, we will use T-film for the external part. Right? So let's actually open, so that's a flow around the cylinder. So let's open the flow around the cylinder here, chapter 7. It's over here. So we'll open chapter 7, and there was this table for a flow around the cylinder. And its Nusselt was some coefficient Reynolds to power m, Prandtl to power n. So it is a cylinder, right? But I have to check the news number before I pick the right correlation for me, right? So now that Reynolds number and will have to be based on the external velocity, right? Not the velocity in the pipe. And it will have to be based on a viscosity. And that viscosity will be evaluated at, no, we'll actually have to evaluate it at the film temperature. I think it was here on the table somewhere. Did it say in the table all properties should be evaluated at the film temperature? The slide above it? Right. So, but also I think in the table you should be able to see this, not on the correlation above it. But does the table itself say the property should be evaluated at T-film? It should. So the air is at 25 degree, correct? So that's T infinity. I need T-film to get my Reynolds number so that I can tell which formula I should use. So, okay, 25 here. What about this guy?
Since we don't have any, you're assuming there's no heat transfer to the pipe inside.
Wait, we assumed the conduction is neglected, right? So when we assume that the conduction is neglected, then we short circuit this part. We assume that the outside and the inside of the cylinder are the same, right? There is no resistance between them. So if this is TS, then this is also TS. But what is it? What is that TS? I can't hear you, Jose.
Somewhere between the two.
Right. So I was worried that you would say it's 325. If you say it's 325, then you are neglecting the convection inside. And if you assume it's 25, you are neglecting the convection outside. No, you cannot neglect either one of them. So some place in the middle is actually more accurate. Right? It's not 25, it's not 325. All right? So let's assume 100. Why? I guess because that's the answer. So, well, so of course you can assume it wrong, right? This just make the solution longer. So let's assume someone would say, well, I think it's at 50. And you get the properties at 50. And then he calculate the temperature. Eventually you can calculate the temperature to check on your assumption. Yes, it's not required to calculate the temperature. What we wanted was a Q. But you have to check on your assumption. Anytime you assume something, you check on it. So we assume 50 degree and we calculate and it's 80, for example. That's not a good assumption then. Then you have to revisit again and say, let's assume 80. Right? Get the new properties, get the new Reynolds number, get the new Nusselt number, get the new H, get the new Q, and from that get the new temperature, and then tell yourself, is it 80 or not? And if it's close, then you basically call it a day and say we are done. If it's still far away, you do the assumption again. Right? So I know you don't really like try and error in the exams. So let's hope there's not that many problems like this. But if you assume TS equal to 100, then T film become 25 plus 100 over 2, that's 62.5 degrees C. And then my table actually is like 60, 70, so I don't want to interpolate in my table, especially that I'm the one assuming the temperature. Why should I assume a temperature that give me a lot of headache to start with? So let's just call it 60. And again, we will check on that assumption, and if we are close enough, we are done. All right? So what I'm saying is assume something that's also convenient for you, something that makes sense. Not 25, not 325. Right? But also something that's easier to get in the table. So I guess the closest line that you don't have to interpolate through. Right. And you get the new 189 10 to minus 5 meters squared per second, the Prandtl 0.72, the K 0.028 watt per meter Kelvin, and then we calculate the Reynolds number Vd, so V infinity d over nu, and it's 1.05 10 to power 5. And from this guy, it's almost 100,000. We go to our table and say for Reynolds 100,000, which line should I use then? Yeah, this guy. This is between 40,000 and 400,000. So the Reynolds number, the Nusselt number would be 0.027, 0.027, Reynolds 0.805, Prandtl 1/3. This guy. Okay. So Nusselt is 0.027, Reynolds 0.805, Prandtl 1/3. So we know the Prandtl, we know the Reynolds, so the Nusselt number is 266.6, which is of course H out, D out over K. From that you get H out equal to 149.7 watt per meter square Kelvin. All right? So we are done. We have H out, we have H in. and the Q dot is T P mean minus T infinity over 1 over H out area out plus 1 over H in area in, after neglecting the conduction inside. So 325 minus the 25 over the, so by the way, that area is the same as that area. Actually, we can take them from here and just write them here. Correct? And so that area is, of course, by dl, and that L was 1, because we are doing it by unit length. Right? And 1 over HI is 50, 1 over 149, and the whole thing become 1766 watt per meter. Okay? So how about our assumption? We assume that TS, let me put it in red here. We assumed TS was 100 degree. Almost 100 degree. How can we check that assumption was correct? Can anyone calculate TS for me? Anyone? I can't hear you, Jesse.
Take a Q and plug it back into the previous equation using a slice from 25 TS.
So just tell me Q dot is equal to, this is T infinity.
225.
T infinity, you are going to go from the inside? Okay. So T bulk mean minus TS over
H, 1 over H.
area I, correct? You have HI area I, so Jesse basically did it only for this part. He said that Q through the whole thing is also Q from the fluid to the surface. So T bulk mean minus TS over 1 over HI area I. And so from this, the Q is given, the HI is given, T bulk mean is given, the only thing is TS. So you will get TS, and not really surprising, it's 100 degree. So the assumption was perfect. So
And if you were to assume a different number, you'd have, this wouldn't come out to the same thing.
so really right. So what's really important is, so don't panic if you assume 90 and you get 100. Should you really go and reiterate again? How could you tell whether it's worth it or not? It's the effect on the properties. If you look at the viscosity at 90 and the viscosity at 100, and you would see that those two numbers are the same, the Reynolds number will not be that much different. You will get the same correlation. You'll end up landing on the same correlation. And then the Branton number is almost the same, and the K is almost the same. I will end up with the same H. Why should I go again? So it's not really how far the temperature is, it's how far the properties is. Now, if you have another really weird fluid that has huge variation in properties, so maybe at that particular case, 1 degree would be a big deal, because the viscosity change a lot and the K jump, and so it's really the property that tell you whether you should go again or not. Okay. Eric, you have a question? Okay. Okay, now I would like you to look at this equation here, because that's the next chapter. So in this pipe with this external resistance and internal resistance to heat transfer, basically, let me return back the area to its place. So that Q dot, which was delta T over 1 over H out area out plus 1 over H I area I, this can be written as Q dot is equal to TB minus T infinity over 1 over UA. So this guy would basically be this plus this. It's kind of the total resistance, but it's expressed in the same units as the H. So the H was a convection heat transfer coefficient. The outer surface convection heat transfer coefficient and the inner surface convection heat transfer coefficient. That U, we would call it the overall heat transfer coefficient. So it's basically the end product of this heat transfer problem. That's the total resistance kind of to the heat transfer. All right? So for this pipe, transferring heat from one flow to the other, the whole thing can be described by that overall heat transfer coefficient. Okay? And so that number is all you need to know. If someone gives you that number, that's really convenient because you don't have to calculate the convection from the inside or the convection on the outside. That's basically just, here is the total resistance to heat transfer. All right? Even if there is a conduction here, ln R2 over R1 over 2 pi KL, even this is lumped in. So at the end of the day, the Q is UA delta T. Where this U, so I rather than 1 over UA, I took it upstairs, and so now it's Q is UA delta T. That is the equation for any heat exchanger. Any design that's turning the flow, the heat from one fluid to the other, can be described by simply Q is UA delta T. Of course, that U has convection and conduction and convection. And those two convection could be very complicated. The conduction could be multiple layer. You know, the wall could actually have coating from the inside, or have not nice coating, but maybe bad coating. Maybe it's mud from the river that's basically depositing on the inner side. But at the end of the day, the pipe could actually be multiple layer. And that's all the conduction. So conduction 1 plus conduction 2 plus conduction 3 plus the convection on the inside and the convection on the outside. Okay? Okay, let's just solve in the next 10 minutes one more problem before we go to the heat exchanger. So this problem there is steam condensing on the outside. So we have a whole chapter for condensation, boiling and condensation. But you should basically know that if you have condensation, it would happen at same temperature. So the steam would be condensing and turning into liquid, from vapor to liquid, while both the steam and the liquid, both the vapor and the liquid state, they are all sitting at the same temperature. So T infinity is 120 degree. So of course that temperature, why it's not condensing at 100 degree? I thought that water was boiling at 100 degree. Why 120? How is that possible? The pressure. There is a whole TS diagram associated with this, right? And so really it depends on the pressure. The pressure where this thing is at, that's when it will boil, right? So if it's 1 atmosphere, this is the TS diagram. So your pressure will determine when you would be boiling, right? So in power station, usually the condenser is actually at like very low temperature. They like to make it condense at very low temperature so the turbine have a lot of room to expand. The steam in the turbine expand from the high pressure in the boiler all the way to the low pressure in the condenser. So the lower the condenser pressure, the more space you have for the turbine to run, right? Huge expansion mean a lot of work you can get. So they take the pressure in the condenser as low as they can. So it's not at 1 bar, right? You know what kind of pressure would be in the condenser? Regular from your thermo 2. You had your thermo 2 yet? No? So how low do you think the pressure should be? What's your guess? Just a smart guess. So what is the temperature in the condenser you think they can cool down the condenser to? What is the lowest you can ever dream of? If you don't remember the Rankine cycle, there is this turbine, condenser, and then a pump, and then the boiler, and then the turbine. And of course there are a lot of feed water heater in the middle and stuff, but that is the basic cycle. So how cold can this condenser be? What's your dream from heat transfer point of view? How cold you can bring the steam to? Why did you say that? James said 20 degree. Why 20? Right, so that's what I was looking for. That the lowest the condenser can be cooled to is the air temperature. Because we are cooling the steam with our air in Tulsa, our water in Tulsa, right? We will just air cool it, or we will water cool it from the Arkansas River, or we'll just dig water from underground and cool it, right? So over here in Jenks Power Station, they cool it with cooling towers. So basically the water cannot be cooled less or lower than the air that's cooling it. Right? So if we are at 90 degree, we cannot make the condenser cooler than 90 degree. At 90 degree, that would be the dream, and that requires huge area actually. So probably the condenser will be sitting at 120. So if he has 120, that means that the pressure will have to go up. That means less work available for our turbine, because we cannot take the pressure down. So the pressure is set by the temperature we are cooling it at, right? And the temperature is related to what is the cold fluid temperature, which is the air in Tulsa, right? So now you're saying to yourself, oh, those lucky guys in Canada, right? Because they can cool it really, really low. They can increase the availability of their fuel, basically, because they can put the condenser very, very low, right? So anyway, so he is cooling at, so that explains why it's 120, not like 40 or 20, because the air outside couldn't be that cold, right? So we are cooling this by our water, our cooling water. And so that cooling water, again, it's from the cooling tower. I think I might have a picture for you for the cooling towers. We actually went to a trip 2 weeks ago to Jenks in my other course, and so we took those pictures. Oh, you don't see it like this. So. So that's the Arkansas River, and the water coming from the condenser come here, go to those cooling towers. This is the place where they dump the water on basically kind of a tray, PVC tray, and then the air, there's fans over here that suck the air. The air comes from the side, those are the inlet filters basically. The air comes, hit the water, cool it, and then leave. Right?
Why is it so far away from the actual power plant?
You tell me. Well, you would like to use very cold air, right? And so the power plant, the boiler is probably hot. So it's like you don't really want the exhaust of your kitchen to be near the HVAC condenser, right? You want it to always have fresh or cold air near the condenser. Right? But it's not that far away. That the power plant is actually, I'm taking this picture from the power plant. I was actually standing on the over here. This is the supply pipeline. So the students looking at the. So see, if you are here, you can see the tower, cooling tower at the bottom. Right? And so that's the other unit. So this is a boiler. The boiler is like 10 floors hot. Right. So that boiler is really hot. The stack is stack is very, very hot. Not very, very hot, but 100 and something. So why do you wanna make it really close? All right. So for our online student, I guess that is the cooling tower. All right.
How many students are doing
Huh?
How many students are doing that one?
3. One of them is, they are not here in town. So anyway, so the steam is sitting at 120, while the cooling water coming from the tower, the cooling tower basically is coming at 40 degrees C. All right, so that's a cold winter day, I guess. And it's coming at 3 meters per second. And the pipe diameter is 2 centimeters. Again, he didn't say, is it the inside diameter or the outside diameter? And he never said what kind of pipe it is. So same trick. We don't know the dimension. He didn't give us the key. There is no way we calculate the conduction resistance. So we'll just assume neglected conduction resistance. Neglecting the conduction resistance. All right? So what does he want from us? He would like to calculate the Q. Determine the heat transfer from the steam pass to the water flow. And the delta T cooling water. So this is T inlet, there must be T outlet, T exit. He is wondering what is this T exit. Or basically required is Q and T exit. So how we are going to do this? Let's start with the Q. Can anyone tell me how can I calculate my Q? Steam outside at T infinity. And by the way, that steam outside at T infinity, we were never given the velocity. It's not like steam is flowing at 5 meters per second or anything. He just said that's a steam pass. So
Does that mean you just assume the velocity is 0? It's just sitting there?
it's just sitting there, right? And actually, by the way, when we take this chapter at the end of the course, you will realize that the H, so there is an H, there is a heat transfer coefficient, just like for convection, you can get H also for boiling and condensation. You realize that this H is so big, so huge. Right? We'll have formulas for it and we'll know how to calculate this. But it's really very, very big. That's why they love it from heat transfer point of view. They love to have one fluid, rather than just air cooling air, they love to have one fluid boiling or condensing. It takes a lot of heat and it's at constant temperature. So the H is so big that we can assume what? Excellent. TS is also 120. So you neglect not the condensation outside, you neglect the resistance, the heat transfer resistance to condensation. Why? Because compared to the other convection, the inside convection, it's very tiny. Right? It doesn't mean that it's always 0. We will be able to calculate it, but it's really, really small. Just like the conduction is really, really small compared to that convection. So now the Q dot is the T infinity minus the T bulk mean over 1 over H out area out plus ln R2 over R1 2 pi KL plus 1 over HI area I, and I'm going to neglect this guy. I will say it's very, very small, and I will neglect this guy also. So actually, rather than saying 0, you know, a more accurate way is to say what?
Like if we have a surface, we don't need the outside without a surface.
Right, but if I write TS, Miller is suggesting why you are writing T infinity. Let's just write TS minus T bulk mean. Yes, if I write TS, then I will just say TS minus T bulk mean over 1 over HI area I. That would be the correct equation. But if I say T infinity, I have to write those two resistance because they are in the way. From T infinity to T fluid, those two guys are in the way. Right? So that's the right equation. But I'm going to neglect them, and rather saying they are 0, I would just say they are, yes, I would say, how can I write this? It's better to write it, it's much smaller than the inside, correct. So we will say it's much smaller than HI, area I. So this much smaller, those two smaller than mean much, much smaller. And I told you this joke about this, right? That I had one time one grad student, and he was supposed to pick his equation in one of the simulation, and the simulation said you use that model if the unit number is much, much smaller than 0.1. So this equation, you use it if the unit number is much, much smaller than 0.1. Well, it turned, so I was checking his calculation. I told him, why did you use this one? And he said, because the unit number was 0.95. 0.95 is not much, much smaller than 1. Let's call it 1. Right? It's not much, 0.95 is not much, much smaller than 1. It's just smaller than 1. When they say much, much smaller, it means, right, 0.001, like it's really, really small, you can neglect it. So when I'm saying much, much smaller, I mean really small. It's not like 1 and this guy is 0.5, so let's neglect it. No, this one is 1 and this one is 0.01. Or 0.001, like 10%, 1%, like really small.
Could you explain why we're neglecting 1 over H?
So I cannot totally explain it because we haven't seen the equation that we calculate H out yet. This will be a chapter later on, but I can tell you that this H out will end up being very, very big compared to HI. You just have to believe me right now, because I didn't show you the equation. But if H out is really, really big, so let's imagine HI would be, let's imagine that HI will end up being 12,000 watt per meter square Kelvin. H out will be 120,000, not 12,000. So it's like 10 times bigger, for example. So if it's 10 times bigger, that make 1 over H out.
How is it 10 times bigger?
So that's the part that I cannot show you. That's the equation that it's a whole chapter.
And how am I going to see that?
So that's a valid question. So Ariana question is like, if this show up in the exam on Monday, why would we neglect this resistance on the outside surface? And the reason you would neglect this one, because it's condensation. If you have condensation or boiling on one side and convection on the other side, you should know that condensation is much more effective heat transfer mechanism than convection. So as a result, his H will be order of magnitude bigger than the H of the convection. That make its resistance order of magnitude smaller than the resistance of convection. All right? Just like, why did you neglect the, let me ask you this, why did you agree to neglect the conduction resistance? You were okay with neglecting this, why?
Because we have more convection than conduction. We have 2 of the convection than convection.
So partially because we know that the conduction is much smaller than convection, right? And partially also because we didn't really have a choice. We didn't know the K and we didn't know the diameter. How we are supposed to calculate the conduction? Well, same thing on the outside. This particular problem, you didn't really even know the velocity on the outside. How you are supposed to calculate the News number and treat this as if it's convection, for example.
So,
You were not giving the tools. That's for practical purposes. And physically, you should know that conduction is smaller than convection. Conduction resistance is much smaller than convection. And also, boiling and condensation is much smaller than convection.
So with, in the future, when we have boiling or condensation on the outside,
Right.
assume H out is always going to be negligible.
That's excellent question. And let's extend Brandon's question to conduction even. So in the exam, if you are given, so his question is later, once we know those H's for condensation and boiling, and we have the correlation, we have the chapter available for us. And even conduction too, next Monday, if you have the conduction resistance, you were given the K and you were given the resistance, the R, all the R's. Should you neglect the conduction next to convection, or should you calculate that?
I mean, if it doesn't really matter whether it's going to hurt,
So,
just to be safe.
so Brandon is saying, well,
Just like
but you would feel really,
you were
you
given
you would feel very silly if it's actually, if convection resistance is like 100, and then the conduction next to it is 0.001. And you'd say, okay, now it's 100 plus 100.001. Okay, now let's, and you spend like 50 minutes, not 15 minutes, trying to calculate the ln R2 over R1 over 2 by KL, because you had to interpolate to get the K because you didn't know the temperature. And so that's a good question. And so if, however, by the way, if the pipe is really big and it's not really that thin, or if the K is not that small because the pipe is not copper, the pipe is, I don't know, plastic or something that's not really that good conduction, it's not always neglected. You just have to look at the number and maybe make a visual inspection to say, does it worth it? Do I have the time in the exam to calculate this or not? And in real life, by practice, you would know that you would do this calculation many times, and you know, this pipe wouldn't matter. Let me just go for the, where is the beef? Right? And the beef would be the convection. You don't want to add the 0.001. So you will get that sense, which one is really the biggest resistance. Right? Okay? Okay, we are okay with neglecting those two resistance? Right? Because we are assuming their H's is so big, the K is so big, that they make those two resistance very small compared to the other one. All right. So now, how we are calculating the Q? Delta T over HI area I. 1 over HI area I, right? So we have to calculate HI. So we have to calculate the Nusselt number. So we have to calculate, huh? Right, we have to find the News number, and therefore we have to find the properties. All right? So that we can check the News number and make the right equation. Laminar, turbulent, liquid metal. It's not liquid metal, it's water. Right? So, how about the properties? What temperature should I pick the properties at? No. Because why not 40?
yeah, yes.
Because 40 is the inlet. And I bet the outside, the outlet would be higher than 40 because the steam is at 120. So it would be a long route to actually just assume it's 40. But if you assume higher temperature, you will basically get a better, you'll get a head up, basically, head on in the calculation.
Is there a way to solve this mathematically, or do we have to guess like the temperature and find the average?
So at this stage, you can actually guess the temperature by, I guess, guessing an H. If you have solved problem, or you open textbook and you find what's the typical H they have for such velocity, you can use this to calculate, guess a temperature at the exam. All right? But, so in this problem, actually, the T exit will end up being 56. That's the solution. So if you assume something between 40 and 56, you will have an early or head-on in the problem. If you make it closer to 40, like 45, you know, you may have to do it again. All right, so anyway, so you calculate the Nusselt number and you'll find that it's turbulent. And this time, the Nusselt number would be 0.023 Reynolds to power 0.8 Prandtl to power, remember it was 0.3 for cooling and 0.4 for heating. This time we are heating the fluid. Alright, so it's Prandtl 0.4. And you calculate the H from the Nusselt, so that Nusselt is HID over K. And from that you calculate the H, and from that you calculate the Q. And from that Q, so that was the first thing. And you can check on the temperature. And actually, the temperature is also required anyway. So even if you don't want to check on your assumption, he actually asks you to calculate the temperature at the exit. Right? So we assume T bulk mean. We assume what is the temperature in the middle. And we said 40 is not a good...
So anywhere between 40 and 120.
Huh?
Anywhere between 40 and 120, but more close to 40.
Right, and probably it's not 120. It should be closer to 40, right? And so what temperature you will assume at the beginning, that will make your solution even longer or shorter, depending on how good the assumption is. Right? Of course, the easy version of this problem is I give you the temperature, ask for the Q. Then it's piece of cake. But in real life, you don't really know the temperature at the exit. That's why you have to assume. All right, so anyway, we have to check on our assumption and we have to calculate T exit. Someone need to help me. How can I calculate my T exit and check that that assumption that I started with was good? Can anyone calculate T exit for me?
Same way we did earlier.
What do you mean?
Solve for Q.
We solved for Q. We had the Q already. How did I get the Q? I get the Q because once I know HI, I said, once I know QI, what I'm going to do, I'm going to say that Q dot is HI, area I, T infinity minus T bulk mean that I assumed. Right? So I get my Q. The Q end up being how much? The Q was 61 kilowatt per meter. So this was done per 1 meter length. All right, I have my Q. Anyone? T exit. How can I get T exit?
You have to solve for your T base.
So this is what we assumed, right? We assumed what is the average temperature in the middle of the pipe, or the bulk mean. I didn't tell you what I assumed, right? I actually assumed 40. So that's like I'm really going for a try and error here. If you assume the inlet, you are really going for a try and error. Right? Because you know it's not 40. It probably will have to be higher. But in that situation, they assumed 40, and they got that Q. All right? We want to check that 40 they used over here is correct. For a free homework, delta T logarithmic mean?
Yeah.
What do you mean?
Isn't that the same thing as T infinity minus T V? You're setting Q is equal to HI A. It's equation.
So let's answer your question after first someone give me the... Jesse is saying, why did we say T infinity minus T bulk mean. Why you didn't say ln, sorry, why you didn't say that the Q is HI area I delta T1 minus delta T2 over ln delta T1 minus delta T2? Because that's more accurate. It is more accurate. And this is approximation. You say it's the average temperature in the middle, that's an approximation of this equation. We know that. But I will answer that question after someone first give me T exit.
What did it do with equation 814?
What is that?
Q equals m dot Cp Te minus Ti.
And you have a free homework. So Jose said that Q that you just calculated, that kilowatt, that's coming from HA delta T or the ln delta T, whatever delta T we are going to use, that Q coming from the heat transfer, HA delta T, is going to go to the water. Right? Those Q are going to the water. They will heat the water. They will increase the energy of the water. And therefore, it is m dot Cp delta T of the water, T exit minus T inlet. You know T inlet is 40 degree. You know Cp, you get this from the table. Table at what temperature? At the assumed average temperature. A T bulk mean that you are assuming. And m dot, how can I get my m dot?
Rho AV.
Rho AV, and it's, he gave us the velocity. I deleted that, but the velocity was given to us. It was 3 meters per second. We were given the velocity, we know the area, and we can get the density at that bulk temperature, bulk mean temperature. So it's rho AV. All right? So you get basically from that T exit, which is turned out to be 56 point C. And then you question your assumption of the temperature that you assumed. Right? You question, was I right to assume 40 or not? All right? So now, JC question is, why when you said the Q is HA delta T, why did you use it in that form? Again, that form is approximate, and JC is right. The more accurate way is to say, so here is T inlet, here is T exit, and here is TS. This guy is sitting at 120, and this guy is sitting at 40. Actually, sorry. Yeah, this guy is sitting at 40, and this guy will go to 56, which we don't really know yet, but it's going to go to 56. So you will have to use this logarithmic mean temperature difference if that delta T1 and delta T2 is less than, is actually more than 40%. So basically, this difference here is 80 degree, and this would be 64. And so the difference between them is 80 minus 64 over 80 times 100%. So it is 20% difference. So 20% difference is less than 40%. So the mathematical average is not going to make a lot of error. If that difference is bigger than 40%, you have to use the logarithmic mean. All right? So 40% is the criteria for forcing you to use this. All right? Does this make sense? So we are okay using the logarithm, the mathematical mean. It wasn't good.